My name is Eric Gebhard. I'm with Signal Microwave, and I want to talk to you a little bit about how we use COMSOL, is what we consider a core technology for development of RF connectors and high-speed digital connectors. Signal Microwave, who are we? Probably most of you haven't heard of us. We're a new company, and we design and manufacture high-frequency coaxial connectors. We were founded in 2014. The founders, the owners, have many years of RF experience, both in RF systems and in coaxial connector design and simulation. And from the very beginning of the company, we've used COMSOL has been at the heart of everything. It's really been where we wanted to start the whole everything on the design. So real quick, I'll just kind of talk a little bit about our, so you have an idea what kind of products we do make. We make edge launch connectors. These are mounted on a board, as you can kind of see on the one in the gold on the top there. They mount on the board, allow you to get a signal onto the board. We have various different sizes. These are part of the COMSOL parts library. So if you're doing a simulation and needing them, you can actually just drop it straight in on the parts library, and the domains are set up so you can configure the parts very nicely. We also do some vertical launch connectors and some field replaceable connectors and such. I won't bore you too much on those. So where are RF test connectors used? Well, they're kind of used in a lot of different places. High-speed digital industry uses them quite a bit. Test equipment, test labs use them. Wireless, the 5G systems are using them. They're pushing the frequency that they have to do between base stations much higher than they are now, so they need to start looking at higher frequency, higher performance test connectors. The military is kind of a traditional customer for these. Chip makers also use them a lot. They, when they're developing a new chipset, they make evaluation boards to send to customers to try and get them to buy them. So why are they important? Well, what they really are is they're the window. A test connector is a window between your device and the outside world. So if you have a hazy window there, the world's not going to see your device. You're looking out at something, and it may not be, it may be the greatest thing in the world there, but that your customers can't see it. They just see this blurry thing. So you want a clear window there. You want this transparent connection so that the world can see what you're making and doing very clearly. The details are lost. If you don't have it if the customer doesn't have a clear view of your part, the details are lost when the connection's not clear. So for us, COMSOL has been a core technology as the business. All our products are designed in COMSOL. All our connector products are designed there. Currently, we're using the RF module and the live link for solid edge. Simulation has been in part of our initial business strategy. Right from the beginning, this was the strategy we wanted to take because we needed to reduce our time, to keep the time to market down and keep our development costs low. And as a small business, those are critical. You have to be very efficient with your resources, and so having using COMSOL has really been a critical factor to our success. So let me just walk through that a little bit. And you probably all have seen this design process. It's pretty basic. You start with an idea. Someone, engineering, sales, customers, someone comes up with an idea that they want something. And you simulate it. You create this simulation to figure out how to make that, how to come up with that from your concept. And you go and you build your prototypes to see if, you got your simulation, you make your prototype, you make your drawings, you make your prototypes. Finally, you got to test it. This part of it's pretty easy. You can, as an engineer, you can design, you can kind of estimate where you go, how much time it takes, what it's going to do. Problem is when that testing goes bad. All of a sudden, you're back up to the simulation end. to the start. You got to fix that. You got to go through an extensive failure analysis. You got to go through. You may have to recorrelate your simulation results. You have to make new prototypes. You got to do more testing, and it just delays and increases your costs, and that's a big problem. What COMSOL has helped us with is we've been able to really eliminate that design iteration cycle. It's really been there because it gives us a very solid model of what we're looking at doing, and we can take that model pretty much straight to, almost straight to production right from the prototype. So, it gets us to production, and that, of course, makes everybody happy. It's what everyone wants. So I want to talk a little bit about a couple examples of products that we've developed and using COMSOL, and kind of walk through how it's helped us on that. So our first example is for a company called Vaughn Test. We did a custom design connector. Vaughn Test makes automated test equipment for the integrated circuits, for circuit boards, wafers. Very, very fancy equipment. It's all robotic controlled. They can load things, unload things very nicely. So they came to us and they had a design requirement for a connector system that needed to be mode free through 70 gigahertz. They wanted us to, it had to be able to be automated for a connection and disconnection. So we couldn't use a coupling nut to make these connections because they're doing this all robotically. And so they have robotic arms, robotic platens that are holding these together. They wanted low reflections, low loss. It needed to be compatible with an existing float mount. And the most difficult thing they did for us was they wanted the parts in 8 weeks, which makes this tough, especially when we consider that some of our vendors have 8+ week lead times. So it made it a bit of a challenge. But we took it on, and we did our initial design simulation. Kind of came up with our concept. You can kind of see it over there on the side of the screen. And it looked pretty good. We were pretty happy with it. Just real quick, so you know how we measure things, I mainly look at the S parameters, the scattering parameters. So I'm looking at S11 and S21. And on S11, I usually look at that in the voltage standing wave ratio. It just gives a better resolution for a very low loss passive device. So that's what the black line is our S11. We're trying to get that as close to 1 as possible. So we did that. We ordered the prototypes, and we made prototypes were made, and we tested them. And a little background on that: we were under a tight schedule. I actually flew out on a Friday to our vendor to get the last parts made, and worked with them over the weekend. Sunday afternoon, we got the parts done. I put them in my bag and flew back home. Monday morning, we put them together and tested them, and they didn't look so good. We, as you can see, between the dotted line is what I simulated, the black line is what I actually got from test results. And it was not good. And I'll be honest with you, I used some more colorful adjectives than not good when I saw the results. So I sat back and I looked at what's going on with this. And we found a very we found a machining error in the part that I just picked up. I'll take some of the blame for that because I was in a hurry. I didn't check them fully when I jumped on the plane. So when I found that, I quickly decided, I put that simulation into that, I modified the model to put that into the simulation. And I came up with a very nice correlation between my test results and my simulation. And all I did was really change the geometry, which told me very quickly, I have a nice solid model here. I can predict what's going on. And I felt very good at that point because I knew when I got the parts corrected, I would have that. And the next day, my vendor next dayed me out some new parts. We built them, we received them, we retested them, and we got a good result. And we were ready for production. We were really happy with that. So, and sorry, I mean, we met the design and goals in development. Once again, we got good correlation with COMSOL. The good solid models that they gave us allowed us to meet that design schedule. We wouldn't have been able to meet it without that. And ultimately, the customer's happy with the design. They're using it in production. I mean, that's what our ultimate goal is on that. Second example I'll run through here is we developed a 1 millimeter connector design. Now, when I refer to a 1 millimeter, let's see if I can do this. We're referring to the inside diameter of the outer conductor of the coaxial line. So this little section right in here is that diameter is 1 millimeter. So it's a very small diameter. But that gives us is high bandwidth. So we can go from DC to 110 gigahertz. We decided the decision to make this connector was done in about February of 2017, and we wanted to release this at the International Microwave Symposium show in June of 2017. So we didn't have a lot of time, and we had a lot of little pieces to put together on this. And we decided to, since we had to make a board, we partnered with the Isola group for the board laminates, which I do believe the Isola laminates are going to be added into the materials library and here. So those are now in there. So real quick, the design goals were obviously the bandwidth. We wanted to make sure we had DC to 110 gigahertz bandwidth. We looked for low VSWR, which is that voltage standing wave ratio. We wanted it less than 1.6 to 1 on a test board. And to test these connectors, we actually have to put the connectors, as you can see up in the top corner there, we have to put the connectors on a board to test them because there's no way to interface with the backside. The backside's totally designed for to mount to a board. And we wanted this to be a solderless connection. So we started with the board interface. That's really where we can do the most design work on this design, because the interface, which is the threaded part up on the top where the cable would connect to it, is defined by standards. IEEE 287 defines everything. It tells me the diameters, the tolerances, everything. So I can't really change anything there. But on the board side, I have a lot of options, and we ended up going with a smaller pin than we normally do. Our normal pins are about 6 mils diameter, so fairly small. These ones we had to drop it down to about 4 mils diameter, so extremely small. But it matches better with the thin substrate that's used on these. I think the substrate we were using was 5 mils thick, so very, very thin, 0.005 of an inch. It's a very thin substrate. I put together this simulation in COMSOL using the RF module and LiveLink for Solid Edge to develop it. And I don't really have a lot of simulation results to show because I did this for optimization. I didn't really do the simulation for correlation. I did it for optimization because there's too many parts and it makes such a big model to try and do everything together in one shot to get that it just made more sense to break it up into pieces. As I said, we worked with the Isola group on the board material, so they spec'd out their Astra MT77 material, which works through 110. It's got nice stable decay. And they measure it at 10 gigahertz. It's about 3.0. The thing was, we were going to a much higher frequency, and we wanted to know what that higher frequency, what it was going to do there, so we had the right material properties for the simulations. And we used the free space method to measure this. If you're not familiar with that, it's basically you have a horn, a reflector, it goes through the material, another reflector, it's received, and then you can measure the data, the signal, and you can extrapolate the decay out of that. But it's a nice material, it's low loss, easily processed. So, as I said earlier, the big kind of the exciting part of this whole thing is where it matches up with the board. How do you get this signal from a round coax to a rectangular board? And it's the problem of trying to put a square peg or a round peg into a square hole. It's not always a clean effort. So we designed this. We wanted to make sure this was top ground only, so that you could build a multi-layer board setup. No one really builds single-layer boards. They mostly do multi-layers. So you have your RF layer, you may have power layers, digital layers, multiple layers. I've seen 10, 15, 20 layer stack-ups from people. We designed both a microstrip and a grounded coplanar waveguide launch. These are just different transmission signal types that we did to accommodate for what our customers would need. And we use the microstrip. We use a little grounded coplanar launch structure just to enable a top ground structure. That's kind of what you see down in the bottom. You see we have the top ground, and then there's a set of vias using to transfer the ground from the top to the bottom. And the board launch was simulated using both the connector and the board. Once again, as I said, you got round and kind of rectangular. You have to do this in 3D. You can't do this as a 2D system. It's got to be done in 3 dimensions, which is one of the advantages of using a 3D solver like COMSOL for it. And once again, we did we simulated to optimize the layout. We didn't look at trying to correlate the layout. We did it to optimize the layout because it's such it could be a very large, cumbersome model to work from, and you have a lot of variables. If you're trying to optimize, it can get very, very large. So we built them and tested them, and we ended up meeting all our goals. And this was this was our first shot at it. On our first shot, we had the models we were getting were very solid and very strong, and they were giving us good results. So we were able to, we didn't have to go back through that design iteration and make a bunch of things. We were able to meet a very tight goal. We had, the results. We had good bandwidth. Our insertion loss there, the red line, it's nice and linear. We're not dropping off with our bandwidth. The black line, the reflections, the S11, we wanted that under 1.6. We're actually under 1.4, so even better. We're really happy with it. So a quick kind of summary of this. We were able to release it on time when we wanted to at the IMS show in 2017. COMSOL allowed us to do this because we had the solid models, a good, strong, powerful model for it, that we could do it in a short time. Once again, we used kind of with this design, we used more of an optimization versus a correlation design strategy or simulation strategy. And, once again, ultimately, the customers are happy with it. We've been selling them to them. They've been very, very popular with their customers. So real quick, kind of in summary, COMSOL's been at the heart of signal microwave from the start. It's enabled us to develop new designs very quickly with very few design iterations. I mean, it's really, we've only had 1 or 2 designs that I've had to go back through and actually make new parts or change the design because something didn't work right. And so it's been very, very powerful tool for us. These new designs have allowed us to grow quickly. As a small, as a new business, that's key. You want to grow. You want to have some a way to grow. COMSOL has been an integral part of our business and design process, signal microwave, and I don't see it changing. The business is, in a lot of respects, built around COMSOL and using that as a tool that everything goes through. In the future, we got more connectors coming out that we're going to be adding to going to get added to the parts library that we're looking forward to. And on a personal note, I am very much looking forward to this the frequency to time domain transform that is coming out in 5.4. I'm really looking forward to playing with that and using that to see how I can further optimize the process and optimize the designs based on some of the time domain results. So, just want to say thank you for your time.